It turns out that measuring angles in degrees is a pretty arbitrary choice. It was kind of a random choice made millennia ago. Well, there's another way of measuring angles. We use a unit called radians. Now, radians is just as arbitrary, but it's another way of measuring the size of an angle. To give you an example, I could measure the distance between where I'm currently sitting and the front door of this apartment by measuring it in inches. Or I could measure it in miles, or I could measure it in feet or centimeters. The point is that there are many different units, many different base measurements: the inch, the mile, the foot, the centimeter. And then my job is to figure out how many of each of those I need to get from here to there. Well, it's the same thing with degrees and radians. I can choose to measure in degrees, or I can choose to measure in radians. The unit itself is a different size, just like the unit of an inch is different from the unit of a centimeter. Our job is to figure out how many we need to get from the positive x-axis around to wherever our terminal ray is. So let's talk about what a radian is first. Picture yourself holding something round. That's not a very good round shape, but I think it'll do. Your round thing can be anything from the wheel of a bicycle to a saw blade to a CD or an LP. Anything that has an obvious center and which is round in shape. Now imagine that you have a piece of string and you're going to measure from the center of your round thing to the edge. And you're going to use a piece of string to make that measurement, and you're just going to cut the string at the end so that you have a piece of string that's the exact same measurement as the radius of your circle. Now with that piece of string, start wherever you like, but I like to start kind of where my radius ended. Doesn't really matter, you could start anywhere. And start wrapping the string around the outside of your circle. The string is only so long, right? It has the measurement R, and R could be different depending on what your circular thing is. If it's an LP, if it's a vinyl record, it's probably about 12 inches. If it's a CD, it might be closer to 5 inches. If it's a clock, well, it's going to depend on the size of your clock. But it's only going to wrap around so far. And then you're going to have to stop, make a mark perhaps, and then start again. That's a second. Sweep around from where I started. I'm going to make another mark. Now, I'm just eyeballing this. If you had an actual piece of string, you'd be able to do it much more accurately. Let's do another one. And the point we're going to try to make here is, how many times do you think a radius, a string, the length of a radius, can be wrapped around this circle? The answer, as it turns out, is 2 pi. Let's see if we can figure out why that is. We know from geometry that the circumference of a circle is 2 pi r. You might have learned this as pi d, where d is the diameter. But the diameter of a circle is just 2 times the radius. So if I replace this d with this 2r, I get the same thing. Now, if I divide both sides of this equation by r, then I get, on the right-hand side, I get 2 pi. And what I have on the left-hand side is the ratio or the relationship between the circumference of a circle and its radius. Now, notice that these are generic. This is true for any circle. Any circle's circumference divided by its radius will always be 2 pi. What does that mean from up here? Any circle's circumference divided by its radius will always equal 2 pi. A little bit of terminology here. We call one of these sort of partial circumferences. We call that an arc. It's the arc of a circle. And the arc is just as you start to go around the outside, the part that you sweep around, partial, well, the entire circle is also an arc, but partial circle, just from some starting point to some ending point, somewhere along that circle, that's called an arc. And we're going to use the letter S to represent the length of an arc. Now, notice that if I put another radius in here, then I'm going to kind of color in this part of my disc. Circle is technically the line, the curve around the outside. Okay, that's the circle. The stuff inside is not part of the circle. This is part of what we would call a disc. But if I highlight that, then you can see the angle that's carved out by making that sweep, starting with the initial ray, not in standard position, but starting with the initial ray and ending at the terminal ray. We could do this to make it clear that those are arrays. And let me also point out that I was aiming for this first, the length of this first pink segment here, this first pink arc is 1 radius because I took the length of the radius and I stretched it along the outside of the circle. Okay, so I was really aiming for that green mark, that first place where I said that's the length of my string. So that angle, because it is, because it's what I get, it's as far as I can get by going along the outside of the circle using the same length as the radius. We're going to call that a radian, 1 radian. So now the length of this line segment here is a radius. The size of the angle that you get by laying that radius down on the circle is called a radian. Okay, so the radian is the size of the angle. The radius is a distance length, right? It's the length of a piece of string. It's the length of the radius. Now, we decided we were going to call this arc here, this arc length, we were going to call it S. So for the angle that I have swept out there, I can say that the S, the arc length, is equal to the radius because I've got exactly 1 piece of string, 1 radius length piece of string around the circle. So this length right here, even though it's curved, is the same as this length right here, right? So my S in this case, my arc length, is equal to my radius. Let's see what happens if I go to the next radius along. So now I've got 2 lengths of my piece of string that is r units long, stretched along once, and then I pick it back up and stretch it along the outside of the circle again. And now I have an angle that is this size. Right, you can see that where I'm coloring in, some of that is double highlighted because I'm including this angle and adding this one to it. So now my angle is this size, okay? And now I have an arc length. There's the right tool here. This arc length is all the way along to here. So starting from here and going all the way along here, I had to use 2 pieces of string. So in this case, my arc length is going to be equal to 2 times the radius of the circle. If I do it again, go out to this angle and color in that new angle, and recognizing that it's not just this new piece that I want, but all of the old piece as well, all of this one as well. My new angle is this size, and my arc length in this case is 3 times the radius. Each one of these, in this case, this very dark white, this medium white, and this lighter white highlighted segment, if you will, of the disk, each one of these is an angle of 1 radian. Okay, so what I have here is kind of a formula, if you will. I'm building a formula that says the arc length of a circle is always equal to the number of radians times r. So whatever the radius of the circle is, the number of radiuses you go around, the number of radians you go around, is equal to the arc length of the circle. So our formula for this is going to be S equals r times theta, where theta is in radians. It's a measurement in radians. This is an important formula. It's going to come back and we're going to see it many times throughout the quarter. Something to keep in mind as you're using it is that theta has to be in radians. That's how we found this formula. If your degrees, if your angles on a problem are given in degrees, you cannot use this formula. You have to convert it first. We'll come back to that in just a minute. So be sure that the angle that you're working with here is in radians before you use this formula. All right, well, I'm already at 10 minutes, so I'm going to try to do the last part of this video fairly quickly. I mentioned a moment ago converting between radians and degrees. I said if your angle was not given to you in radians for this formula, for example, that you would need to convert it into radians first. So here's how you do that. Since 360 degrees is equal to a full circle in terms of degrees, and we've already decided that 2 pi is what a full circle is in radians, it's fair to say that these two things are equal. They just have different units. So this is in radians. In fact, we don't usually use the word radians as a label. Sometimes you'll see rad. But radians are unitless because they're not actually a measurement as much as they are a ratio. They're the ratio between the circumference of a circle and its radius. So we don't usually use the label. We might have time to come back to that later, but we will still certainly talk about it throughout the rest of the quarter. So if this statement is true, then I can divide both sides by the same amount and get an equivalent equation, right? So let's divide both sides of this equation by 2, and I get 180 degrees equals pi. Now I can take any degrees, any angle measured in degrees, 270 for example, and I can multiply it by 1. Stay with me. I know this is weird, but stay with me. And I'm still going to get 270 degrees. But let's be careful about what form that number 1 comes from. If this is true, then pi divided by 180 degrees, or 180 degrees divided by pi is equal to 1. Both of these are equal to 1. If I want to come out of degrees and go into radians, all I need to do is multiply by pi divided by 180 degrees. And that's going to let me rewrite that. 270 degrees times pi divided by 180 degrees. My units cancel. If I divide by 10, my zeros cancel. And I'm left with 27 pi over 18. 9 goes into both 27 and 18, so I can write that as 9 goes into 27 3 times, 3 pi over 2, because 9 goes into 18 2 times. So the angle in radians, 3 pi over 2, is equivalent to the angle in degrees, 270 degrees. I can do that with nice angles, angles that are we're going to use a lot, like 30, 45, 60, 90, 180, 360, things like that. I can also do it with weird angles, angles that are not so familiar or comfortable. Let's say I had 17 degrees. If I want to convert that into radians, all I have to do is multiply it by 1. And 1 will take the form pi over 180 degrees. My degrees labels cancel, and I get 17 times pi over 180. That does not reduce. So that's my final answer here. 17 degrees in radians is 17 pi over 180. I can do the same with radians. If I have 4 pi over 7 radians, I can multiply by 1 here. This time, though, I'm going to multiply by 180 degrees over pi. The reason is that I want my pi's to cancel, right? And I can do that now because here I have a pi on the top. Use a different color. Here I have a pi on the top of my fraction, and here I have a pi on the bottom. So when I reduce this now or simplify it, I get 4 times 180, which is, let's see, 4 times 0. 4 times 8 is 32. 4 times 1 plus 3, so that's 720 over 7. And that is degrees. I've gone from 4 pi over 7 in radians to 720 over 7 degrees. Now, I don't need to reduce this. This is an exact value, so I can just leave it as it is. There's actually quite a bit more I wanted to do here, but really it would have involved doing some practice converting. So I'm going to leave that for something we can do in class, and converting from degrees to radians and radians to degrees. So that's something that you should practice a little bit before you come to class. And also talking about the important angles, the angles that we're going to be seeing a lot of. And we can come back to that in a different video. We'll see them in class and we'll see them in videos. Just as a very quick, sort of a quick and dirty introduction to that, we have angles in the first quadrant of 45, a little bit less than that, 30 degrees, a little bit more than that, 60 degrees, so 30, 45, and 60. And then we have equivalent angles in quadrants 2, 3, and 4. So we have, come back to talking more about these later, but there's sort of 3 important angles in each quadrant. And from a starting point of here, the positive x-axis, you go 30, 45, and 60 degrees, and then you get to this one. This is 90. And then to that, add 30, 45, and 60 degrees. And then add another 30 degrees to get to 180. Then add 30, 45, and 60 degrees. And then from here, 30, 45, and 60, and so on. And if I do all that arithmetic and label those angles, this is what I get. And each one of these can be converted into radians. 90 degrees, let's see, 180 degrees we decided was pi. That's the measurement we've been using to make do our conversions. 0 times pi over 180 is still going to be 0. So in radians, this is still 0 radians. And if it's 360 degrees, we've gone all the way around the circle, that's 2 pi radians. 90 degrees turns out to be equivalent to pi over 2. 270 degrees turns out to be equivalent to 3 pi over 2. And the other ones can be converted as well. I'm going to pick one at random because I don't want to spend any more time on this than I already have. Let's do 150 degrees. 150 degrees times pi over 180 degrees. My units, and if I divide by 10, my zeros cancel. 15 and 18 are both divisible by 3, so I get 6 here and I get a 5 here. 150 degrees is equal to 5 pi over 6 in terms of radians. So this would be 5 pi over 6. So there's a table in your textbooks that shows all of these conversions, all the degrees and all the radians of these particular angles, and these are the most important ones, and we're going to be working with them quite a lot. You will see others. For example, I think I did 17 degrees on the previous screen, but you will see others, but these are the ones we're going to be working with the most. So it's really quite useful to know how these conversions are done. And I'm going to let you use a note card during written exams. So you might want to put a chart like this on a note card so that you have access to these angles while you're taking an exam. All right, that's way too long for this video, so I'm going to call it quits for now, and we'll go to the next one.